get this going. And I will share my screen. Can you all see that? My
Yes.
browser? Okay, cool. Yeah, so welcome everybody. Talking through the book, The Effect. We're now on chapter 18, Difference and Differences. And let's hop right in here. Chapter fortunately was not extremely long. I don't know. Don't have the hardcover, so I don't know how many pages it was, but it seemed a little bit more reasonable compared to some of the other chapters we reviewed. And so I would call this method, kind of part of what I'm familiar with in the universe of interrupted time series. Um, it's kind of a similar concept to event studies that we discussed last session. Um, there we the difference is we didn't have a control group. There's you're looking at a treatment effect over time with these event studies. Uh, but in that case, there's a before and after treatment. You can kind of take the difference of the effect, before and after, and that's your kind of measured treatment effect. Differences is a little bit more complex in that you do have a control group. I think it's considered a more robust tool for measuring for doing causal inference on observational data. It's pretty common in my field whenever, causal inference is required. I think in public health, it's also very common, the DID technique. Um, and so we have this DAG just representing some of the confounders we're dealing with. The top half of the DAG is what we represented when we were talking about event studies, where you have time as a confounder, and you want to close that, right? The path between treatment and outcome that's going through time, at least partially. Here we do have the time backdoor, but we're also dealing with group as another confounder. One of the issues is you can't close that back door through time entirely, or you don't have any variation left at all. And so in event studies, you kind of get around that issue by constructing a counterfactual, which is like what would have happened if the treated group were never treated at all. And then kind of measuring, what actually happened against that counterfactual. And so again, we need to close these two back doors. We have time and group. And the way we close the back door for groups is we're isolating the variation between the treated and untreated groups separately. So that's kind of a within variation. And then we are also comparing the variation between treated and untreated groups. That's kind of the between variation. That closes the time backdoor. And the basic formula, just high level, what we're looking at is pretty intuitive, right? So you're looking at the treated group, whatever effect we're measuring, outcome variable, the difference for the treatment group, after minus before, and then we're subtracting that by the after minus before for the untreated group. So it's, again, two differences, as the name would imply, difference and differences. So that gets us our effect here. So pretty straightforward there. Any questions at this point? Okay, so the book goes through a couple fairly straightforward examples. The first one was with John Snow and a cholera outbreak that happened around London in the mid 19th century. I'm familiar with this case. I think it's used a lot when people are introducing like visualization tools like Tableau or Power BI, because if you do a map of London against like where the cholera outbreaks were happening, you really see that like, hey, like this stuff's happening close to these wells, right? So maybe it has something to do with drinking water. So yeah, just kind of an FYI there, like, hey, this is a good use case for data visualization. It can help you sleuth how, what's going on here.
I think that
Um,
case is really interesting because I've only ever heard about the data in economics and how this is the
mhm.
perfect difference in differences. And my partner who's in cartography only ever heard about the map, but not about the regression. So I feel like
Okay.
this is an
Yeah.
example that people really like to use, but for very different use cases.
Yeah. Yeah. For sure. And I think, the chapter described this as one of the first times difference and differences was actually used. Um, uh, potentially by Jon Snow, I guess the guy's name was. And yeah, just a little recap of what was going on there. There was the cholera outbreak, and so he's measuring death rates, per capita at two different time periods, 1854 and 1849. Uh, but it turns out he had two locations. Um, One was this Lambeth area that was upstream. Excuse me, it moved upstream between 1849 and 1855. So upstream means kind of upstream of London, which is where we know now after the fact, where a lot of the contaminated water was entering. Um, and so what we're doing here is taking the difference before and after between these, the Lambeth um, company or servicer versus this other area, the non-Lambeth areas or service areas. And what we see is there was a really big decrease in death rates for the Lambeth company between the two time periods, yet we see an increase uh, for the non-Lambeth area, which were more directly impacted by the dirty water in London proper. And so, just taking the difference in differences, we get negative 56. So, that's, if our assumptions hold, that's saying a pretty significant, we would think that would be significant, practically significant anyway, decrease in death rates per capita. Um, if we were just doing this as an event study, where we didn't have a control group, we would just probably take the difference, right? In a really simple fashion, the death rate difference for Lambeth, right? For between 1849 and 1850, and we come up with something like a 45 decrease in per capita death rate. Um, so this gives us probably a better approximation of what the true causal effect was, which is more significant than just the difference for Lambeth. Okay, moving on, one more example. This is trying to give us kind of a graphical view of what difference and differences is doing. I didn't love this particular example, but the idea is in the United States, when you're getting your driver's license for the first time or renewing it, in most states, there's an assumption that you aren't an organ donor, so you have to actively do something, say, hey, I want to be an organ donor for that to happen. So it's not great for encouraging organ donation since the default is you just don't, you're not an organ donor. And so California implemented what was called active choice. And so there is no default. You have to actively say, do I want to be an organ donor or do I not want to be an organ donor? There's no default assumption. And so I think the hope with this program is it would encourage organ donation rates in the state. And so this top graph here, the largest one, is basically showing in white dots non-California states, with this vertical line representing when the active choice was implemented in California. And so the black dots would represent California. And just looking at the raw data in California, it looks like the organ donation rate actually went down a little bit. And so this set of subplots below this is showing a couple lines here. One would be the average organ donation rate pre-treatment. The dashed line would represent non-California states, and then once you cross that vertical line, that's after treatment. And it looks like organ donation rates actually went up a little bit for non-California states, and again, we saw that it went down a little bit in California. So that's the top left graph. And so to do difference and differences, what you want to do is take the difference for the untreated group. It's represented in that subplot in the top right here. We want to calculate the difference before and after. And then in the bottom left graph, they are actually taking that difference for the untreated population, applying that to the California treated population. So now the black line disconnect before and after looks a little bit more pronounced than it did before. And so kind of we measure that, and we get there are differences measurement here. It's a little bit of hand wavy what I just did there, but again, this is just trying to get you a graphical take on how differences work. Again, the same formula that we looked at applies from before. It's pretty straightforward. Any questions on that? Okay, hearing none, I will move on here. One of the big assumptions for DID to work is that what's called the parallel trend assumption, which basically says the difference between the treated and untreated groups would be the same post-treatment. If no treatment had occurred. It's not something that we can actually observe directly, but it is an assumption. And so one of the interesting things with difference and differences is, it can measure some noise, as we would expect in any sort of statistical procedure, right? So the difference in the treated group, what it measures is the true treatment effect plus other effects, right, that maybe aren't related directly to the treatment. So it does pick up some noise, potentially, or just the other effects that maybe aren't noise, but something we're not actually interested in. And then similarly for the untreated group, that difference that we're measuring is really, it's either noise or just other effects unrelated to treatment, because this group wasn't treated as part of this observational study. And so putting that all together, when you're doing difference and differences, you are capturing the true treatment effect plus other effects unrelated to treatment for the treatment group, minus these other effects that impact the untreatment group. So the parallel trends assumptions means that these other effects here cancel out between treatment and untreatment. And so to the extent that they don't cancel out, you have a problem, and you're capturing other things that you don't want to measure in your DID effect. And so the book goes through some tips on how how to go about treating a good control group. One way you might want to do that is just look graphically. This is an informal test. Look for, parallel trends before treatment, essentially. And so the graph on the left here, showing a control group and the treatment group, the parallel trends appear to hold, right? Just kind of informally looking at it, it appears that things are moving kind of consistently pre-treatment, and then not so much after treatment, which is okay. Whereas the graph on the right would suggest that there's some convergence that's happening prior to the treatment, and so that parallel trends assumption may not hold. So a couple other bullets just about like what makes a good control group. You wouldn't want to have a control group where you would expect some sort of sudden change around the time of treatment. You would expect existing trends to continue as expected. No big jumps or leaps, right? Around the time of the treatment. You would want a control group that is at least qualitatively somewhat similar to your treated group, that strengthens your causal effect that you're trying to measure, or makes it more credible, rather. And again, treatment and untreated groups have similar trajectories for that dependent variable prior to the treatment that strengthens your case. And so I just went through the graphical approach to kind of informally assess whether or not you have a good, whether the parallel trends assumption holds and whether or not that control group makes sense for your study. There's also the placebo test. And so what that is doing is you arbitrarily assign a treatment period that's really before treatment. Uh, and so you want to measure if there is a difference in difference effect for that, when in reality you're looking at completely a pre-treatment period. And if you do capture a significant DID effect, you have a problem most likely, with that parallel trends assumption. And then one other thing that you might run into, you may have a treatment group and a control group where the trends are actually exponential. And of course, if you have exponential trends, you're no longer looking at something that's parallel. So in that case, you would want to apply a transformation like a natural log that gets those parallel trend assumptions to hold. And of course, there could be other nonlinear things going on that would require another sort of transformation, but I would think exponential growth would probably be a common one that I would see in my field, right? Because when I think about like insurance claims, they tend to trend over time exponentially, not in a linear fashion. That would be kind of required for this parallel trends assumption to hold. All right, so that's section one of how does it work. Any thoughts or comments there?
Just one thing about the parallel trends that you can't really prove it, right? Like you can
Mm-hmm.
argue for it. But really we're not looking at the trends prior to everything, but at the trends between the counterfactual and the actual thing. Between the counterfactual and the control. So like we can argue for it, but it's mostly about the story, I feel like.
Yeah, yeah, there's definitely some assumptions going on there. Again, they bucket what these checks we're doing with the placebo test and this graphical thing as really informal tests. Um, yeah, so you're right. I mean, this is still based on pretty strong assumptions. As you mentioned, like the parallel trends is not directly observable. Um, yeah, so I think that's a problem with a lot of causal inference, right? With observational data in general. Like, we learned that very early on with the DAGs. You're just assuming you've created, a DAG that reflects reality. And a lot of times, that you just have to kind of go forward with that. It's not something that you can prove that those starting assumptions are correct. All right, so next section is how do we perform DID? Generally, it's the form of a regression. And in a simple case, what you can do is a two-way fixed effects model. We covered that in a couple sessions ago. And so what you could do is you would have a fixed effects for the group, right? Like treated and untreated. Assuming you're really just doing a before and after time, you could have a marker for that or a dummy variable to say this is post-treatment or pre-treatment. And then this B1 effect would be the treatment effect that would be after the difference in difference effect. Just a couple notes of caution from the chapter. You don't need to add control variables that vary by group but don't vary by time. They are unnecessary and they end up kind of dropping out of the analysis. It's kind of a redundant thing to do. But also there could be controls that do vary by time. They can pose statistical problems though. For instance, if these other covariates are impacted by treatment themselves, that can cause some issues in your analysis. So it's just something to look out for. Um, Typically, when we're formulating this regression, it involves a uh, interaction effect. And so this equation here is kind of reformulating what's shown above here. So we would have a dummy for whether the group is the treated or untreated. Well, I guess it would just be a 1 if it were the treated group. Another dummy representing, is this the post-treatment period? And then there'd be an interaction effect on the treated group and post-treatment. And so that B3 coefficient is your difference in differences effect that you'd want to measure. And generally speaking, you're going to want to, best practices would be to cluster your standard errors at the group level. So you wouldn't want to, like if you're using R, you wouldn't want to use a standard linear model to do this. I believe, the fixed effects regressions that were detailed in R code in this book already do that, or at least it's an option to do that. And one thing that wasn't really discussed much here, particularly if you're looking at multiple time periods, not just before and after, is you probably have some sort of serial correlation going on with your errors, right? Because you're dealing with time series and something that you might want to contend with in terms of your errors, right? So you might have like ARIMA errors. When I've looked at kind of interrupted time series in the past, that was something was stressed as something you want to do. Wasn't really mentioned in this chapter, but another thing to consider, I guess, with how you're dealing with your error term. Uh, yeah, and so when we're doing a DID effect, what we're doing is we're capturing the average treatment effect on the treated. I know there's a variety of treatment effects that we've talked about in the past, right? But this is a common one that is measured, and that's what DID does. So just to call that out specifically as it was mentioned in the book. Okay, yeah. So we talked about that parallel trend assumption, and there really aren't formal tests. There are some informal tests. So this section actually kind of repeated how you would go about doing the placebo test. I already described that in the earlier section, so I'm not going to really go over that in detail here. But again, you should also just look at your data as we saw in the prior section, just to see like, does that parallel trend assumption make sense? But if you're doing a regression using the pre-treatment data, you'd want to, again, I guess this is a form of a placebo test. You would want your beta coefficient for time to be 0, right? If you're only looking at pure pre-treatment data, and if you are getting a statistically significant effect, that could be a strong indication that your parallel trends assumption does not hold. Okay. In reality, we might want to get a little bit more sophisticated with our time variable and not necessarily just do pre-treatment and post-treatment. And the reason we might want to do that is because sometimes effects don't take hold initially, right? May take a while for the effect to really be significant, or just the treatment effect maybe dissipates over time. And so one way we can do that is get more creative with our regression, where we'd still have fixed effects for group and time. However, we could have essentially dummy variables for different periods, both pre-treatment and post-treatment. An important thing here is there is a reference level that doesn't explicitly get modeled here, and what they're suggesting here is that like that period immediately before treatment would be your time 0. And then, right, time 1 would be that a period immediately following treatment. Period 2 would be 2 periods post-treatment, and a -1 would be your 2 periods essentially prior to treatment, etc. And so this is good in that you can measure different treatment effects at different times. One thing you want to look out for here, what's cool about this is there's kind of a built-in placebo test in this type of regression approach, right? Because you would expect there to be no treatment effect at all prior to the time in which treatment was applied. But because you're dealing with multiple treatments, you may find some false positives. So the book suggests looking at the coefficients graphically, not just the point effect estimates, but then the confidence intervals as well. And so in this case, this is a DID effect for multiple time periods, where I'm guessing Q2 2011 is your treatment period, or immediately prior to the treatment. We are capturing a statistically significant effect, a couple periods before treatment. And that's, again, if you're measuring a bunch of periods pre-treatment, you may find that. So I guess the idea there is don't freak out if you have a period or two where you are capturing a small, albeit statistically significant effect. Again, you're measuring more things, you're more likely to capture some false positives. But you shouldn't see a systemic issue, right, across all your pre-treatment periods where you're getting a statistically significant effect. And then another call out, using these two-way fixed effects models does not work well when the treatments are applied at different time periods. So like, temporally speaking, maybe your treatment group, maybe you have, just treatment on your treatment cohort being applied at different times. That's definitely an issue. It won't work with fixed effects, but you may see that in the real world. And I guess there's some consequences here when treatment is applied at different times. You may end up getting a negative DID estimate, even though in reality there is a true positive DID effect. And so that's the summary of how DID is performed, again, typically with some sort of regression. Any other comments, thoughts on that? Did I miss anything interesting? Okay. Last section was how the pros do it. This is kind of a similar format to what we've seen in some of these prior chapters here. Uh, the author doesn't really go deep in any of these methods. It's just kind of call outs like, in the real world, things are always messier than you want it to be. Specifically when groups are treated at different times. We just kind of ended the last section talking about that. And the author mentions that best practices are still evolving here. So like, don't take his word for it that these are methods that he calls out are going to be the best by the time we're reading it here in 2025. But one thing you can do, which I found pretty interesting when treatment times vary, is you can center each group relative to the treatment period instead of so you'd end up with something that isn't true calendar time, right? So it's all relative to when treatment took place. And so that way you're kind of centering things appropriately across different maybe treated units, right? By the centering approach. And so he calls out one study from 2020 by Sun and Abraham that does this. And then he interacts, or the authors interact these centered time variables against group membership. And that kind of cleans up the issue, apparently, where you're dealing with treatments at different times. There was also another study by Callaway and Santana that handles things a little differently. It was very hand-wavy in the chapter, so I don't really want to go into detail on that. However, I do think there's an R package that implements this approach. It involves propensity score matching as well. So just an FYI, if you want to go deeper on it, this might be a paper you want to check out. Okay, this is pretty interesting though, like, how you go about picking an appropriate untreated group, your control group. And again, we just talked about this earlier study that used propensity score matching. We talked about that approach much earlier in the book. If you have a lot of different untreated groups, this may be a good way of getting your control. Either selecting only groups that are good matches to your treated group, or maybe using all of your untreated data but just weighting it based on similarity with the treated population. And what you would do here is you would match on predictor variables prior to treatment. So that's a big call out there. You wouldn't necessarily match. You wouldn't want to match post treatment. Another concept that I found interesting, and from what I understand, we're going to be talking about this in a later chapter, is synthetic controls. And so the idea with this is you would not only match on prior covariates, but also prior outcomes. And so when you do this, my understanding is that you maybe have a stronger case for that prior trends or parallel trends assumption that is really important for DID. And so it's considered a good approach to combine DID with matching. There are desirable properties associated with this. In earlier chapters, we talked about doing these regression approaches with matching. It's called doubly robust. And so you can do a doubly robust difference in differences. There's a package for it called DRDID. What's cool about the doubly robust methods is if I think some of your assumptions fail for either matching or the regression, these approaches are, as you would expect by the name, kind of robust to failures of some of the assumptions, and you still get credible treatment effects. So something to check out there. All right, just trying to read what I wrote here a couple weeks ago as I was summarizing this to see if I want to call this out. Yeah, okay. So this is an important point. There could be problems with DID when the treated group was selected for reasons that actually impact the outcome. DID is not going to really help you there. And so matching could be a good way potentially to control for the fact that the outcome that we're trying to measure was related to treatment, right? Like I think an example later in this chapter and in this section we're about to talk about was like, okay, we're looking at unemployment, right? Maybe there's some sort of program to tackle unemployment in a certain city, but maybe one of the reasons the city was selected in the first place is because it had extraordinarily high unemployment to begin with, right? So it wasn't selected at random. So in that case, you might want to control for some of these covariates so that you get a more credible, appropriate treatment effect. Of course, this example that I just talked about can be problematic also because of regression to the mean, right? Again, where you're choosing your treatment group based on how the outcome looks pre-treatment, right? So high unemployment in a particular city might just be the result of random noise or factors that we can't determine easily, right? And so if in the current or recent time periods, you're seeing really, really high unemployment relative to the longer term history or trajectory, it may be the case that in a follow-up period, it's going to go down just because it happened to be extraordinarily high, right? And that, again, could be due to random noise. And so that's called regression to the mean. That's definitely a problem with DID studies in particular. And so there was a call out in the chapter that if you are matching, um, specifically when you are matching like two cities in this case on covariates, this regression to the mean problem really can be significant here. So something to watch out for there. And by the way, the regression to the mean issue I would think would also apply if you're doing an event study too, right? Um, where you don't have a control. Um, when you're selecting your treatment, selecting a group just because you're looking at the outcome pre-treatment, that can be a problem. Um, and so again, with DID, you might be measuring not only the treatment effect, but also just random noise. Okay, this next section was interesting. You can actually apply DID to something other than the outcome variable, which is, I think, the canonical use case here. And so the example that was provided is there's a teacher training program that took place, and the purpose of this was uh, to narrow the differences in test scores between students that come from an advantaged background as measured by income versus students that come from a disadvantaged background where the family does not have a high income, so low income versus high income families. And so we can think of a typical regression where test scores are going to be influenced by income, but what we're really interested in here is a DID effect on the beta 1 coefficient on income. So the before and after effect, the before and after change of this beta coefficient for the treated population minus the before and after effect for the untreated population. And so we can envision measuring this by doing two regressions where we have test scores, we have income, a dummy for after treatment, and then the interaction of income and post treatment. And in this case, the beta 3 coefficient would represent that difference effect, not difference in differences, but a difference before and after. And so if we ran two regressions, one for the treated population and one for the untreated population, we would get two of these beta 3 coefficients, and we could take the difference between those two. That would give us a DID effect for that coefficient. But a better way to do this would probably be to combine all of this into one regression equation. And we can do that here. It gets a little hairy because now we have quite a few pairwise interactions, and with a three-way interaction, whoops, sorry, clicked out of where I was where I wanted to go here. With this three-way interaction, we can actually measure the DID effect directly. I did it again. I have a new mouse and I'm clicking the wrong button. This beta 7 coefficient, which is the three-way interaction between treated, income, and post-treatment period, is actually your DID effect. So I think that's pretty cool that this can be handled all in one regression. It's just a little bit more complicated to look at. Okay, and then the final topic that was discussed during this section was called um, triple differences, or DID-ID. And this is recommended when you as an approach to look at when your parallel trend assumption doesn't hold. And I don't know what your thoughts were about this example. It was a little confusing for me. Um, so give you a lay of the land on the illustration here. So this authors were looking at a time period both pre and post the financial crisis, right, which really escalated in 2008. And there was a policy change in Maryland, the state of Maryland in the United States around this time to help. The idea was to reduce foreclosure rates. And really it just required that the mortgage servicer looked to take some sort of action, right, on some existing mortgages, like they could foreclose on a mortgage, or they could employ some sort of mortgage modification. But we don't have a lot of the details from the chapter about how this worked, but the idea was to encourage action among the mortgage servicer, as opposed to just not doing anything at all. And so one thing the authors considered is, well, we could just take the difference in Maryland. We have examples where this program took place in Maryland. We could compare that against out of state examples out of the state of Maryland, and do a DID effect there. But I guess the idea there is things were really wild during the financial crisis, where things are just, could be very different, very noisy, for one, and then across states, right? Things are just kind of blowing up in different ways. So like Maryland may have been impacted differently than a non-Maryland state. And so what is described as a solution here is we have data both on services that were subject in Maryland to these new policy requirements and ones that weren't. And so essentially you're doing a DID with the mortgage servicers that were subject to the program against non-Maryland states, and then doing another DID with the control group, which is not subject to the requirements. Again, doing a DID with the out-of-state stuff, and so then we're doing another DID with against that initial set of differences. So now we have a DID. And the idea here is that now we're kind of robust to that parallel trend assumption not holding, and that's what the authors did here. Long story short, they found that the modification rates to loans did go up, which is a positive. It was considered a positive, but on the other hand, the mortgage servicers also tended to increase foreclosure rates on houses, which was seen as a negative because the program was actually, one of the intents was to actually decrease foreclosure rates, and it had the opposite effect. Where I get a little confused here, guys, and maybe you can, maybe you shared my confusion, maybe you didn't, is couldn't we have just done a standard DID within the state of Maryland, right? With the servicers in Maryland that were required to do this program and the ones that weren't. They don't really show that like graphically, like maybe because there's a parallel trend issue there, but that's where I would have started, as opposed to just doing two DIDs with the subset of Maryland servicers that implemented this program, and then the ones that didn't, right? It seems a little strange to me that they didn't show us what it looked like if you were to just do a standard DID within the state of Maryland and just ignored kind of the out-of-state effect there. But they didn't really go into detail about it. So yeah, I was left a bit confused by it, but I do think this approach itself is interesting, and it is a tool in our toolkit. If we can't really, apply some sort of transformation to satisfy that parallel trends assumption. Any thoughts on that? Anyone else confused by that?
Yes, definitely confused. I feel like difference of differences is already confusing enough, and if you then add something on top. But I think
Yeah,
sometimes you actually do want that, right? Like sometimes two things are changing at the same time, but you want to know another dimension. But I've never seen that as the main specification of anything because it confuses everybody.
yeah. But with a lot of these as the pros do it sections, the idea again is real world is a lot messier than the simple examples that we look at. So you have to apply more sophisticated techniques. And if your baseline assumptions for the simple techniques fail, you're probably going to have to explore the literature, how to handle your more complex problem, because there probably is a solution out there and probably an R package out there to help you in your journey. All right, so that's the chapter. Um, I do like this effect. It's directly relevant to my field. I think it's a very common technique to use. Um, you can kind of do a napkin math version of this without even doing a regression model, right? Which is also kind of cool. Um, so so yeah, I enjoyed this one, and now I'm trying to stop sharing, struggling with that. There we go. I'm going to put end in the chat, and then we can kind of talk about what the next couple weeks looks like.